Welcome to part 3 of ceramics. Today I'm going to um, concentrate on our discussion on um, glass as uh, a very important part of material ceramics. Previously we talked about structure and properties of ceramics. We talked about traditional and new ceramics. And today we're going to talk about glass, some other important elements related to ceramics. We are going to take a look at some other types of ceramics that we have not covered, and we're going to talk a little bit about the processing ceramics, and we discuss some of the guides or guide to processing ceramics. The picture down here on this particular slide is an important application of glass, and just think about what would the life be without glass. How could we be just sitting there in our homes, nothing or something to protect our windows and doors, but for safety reasons or other reasons, they are strong, and so strong that the material itself would prevent us to see through it. And that's a very important demonstration of the importance of glass. Also, we all, well, most of us, we have cars, and what would a car be without the glass and either the front shield or side, windows and so on. So it's very important to realize that glass plays a very important role in modern life and in modern societies. Also, a light bulb is another example of a glass. Some of you guys may not think in those terms, but it's time to think it through and realize the importance of glass in our today's application. So, what is a glass, and how can we make a glass? A glass really is an inorganic, non-metallic compound. Remember, we're talking about ceramics, and we classify glass as ceramics. So, as a type of ceramic, glass is an inorganic, non-metallic compound, or it could be a mixture of compounds. So it's not just, could have more than one, and it cools to a rigid condition without crystallizing. So in order to bypass that crystallization, we need to cool it very quickly, or have a process in which it doesn't allow the crystallization. So as a matter of when we look at it as a state of matter, glass is a non-crystalline structure of a solid material. If we let crystallization or crystals to form, then it's going to interfere with the clarity of the glass. It's not going to be as clear as we want it to be. Of course, for some applications, for privacy reasons, we intentionally want the light to go through, but we don't want the clarity to be in such a way that it can see through. So that's why we use other types of glass. But in general, as a basic definition, and this is important because if you would be asked in an exam, what would be the definition of a glass as a type of ceramics? It is basically a non-crystalline structure of a solid material. So how can we make glass? The glassy state occurs when we do not give it enough time from the molten state to the final state, room temperature, to form a crystalline structure. So we try to prevent that. If we prevent that, of course, we need to have the right material. Then we are going to have glass. So, what is the most important ingredient in glass? And that is, gives us to gets us to silica. Let's talk about silica. SiO2. Silica is the best glass former, somewhere between 50 to 75%, sometimes up to 80% of silica is used in a glass product. This is of the total chemistry. We like silica because just the material by its nature would transform into a glassy state upon cooling from the liquid. Here's the major difference. Most ceramics, they crystallize upon solidification, but silica doesn't have that property. So we're using that. Of course, we're using other material for other reasons in glass, and examples are sodium oxide, calcium oxide, aluminum oxide, magnesium oxide, potassium oxide, lead oxide, boron oxide. Why do we do that? Because some of these materials, they act as a flux. Flux is nothing but promoting fusion during heating. Some of these material, they would actually help in the molding process. Some of these material, they would actually improve the chemical resistance of the glass against different environmental effects, including acids, basic substances, or water. Some they add color, and some they would actually, very important, alter the index of refraction for optics, the glasses that are used commonly in optics, and so on. So glass is a very important material, and it plays a very important role in our technologically advanced society, and I cannot emphasize that enough. So some of the glass products: window glass, containers, cups, jars, bottles that can be found in any home, light bulbs, the equipment we use in laboratories, the laboratory glassware, flasks, breakers, glass tubing, and so on. Glass fibers, including fiber optics, insulations, optical glasses, including lenses, and the list goes on and on. So, was a glass ceramic. When in glass ceramics, we're less concerned with the see-through properties that we want to have. We are now concerned more with the strength, because the application is now going to be different from the glass that we use in our windows and other material, other applications that I just went through, to the glass ceramics they use as ceramics, tiles, and so on, walls, floors, and what have you. So, how can we produce glass ceramics? A ceramic material produced by a conversion of glass into a polycrystalline structure through heat treatment. Now, we want to have many crystals forming in our structure, and we can achieve that through heat treatment. Remember, we wanted the glass to cool off very quickly from the molten state to its solid state without actually going through the process of crystallization. And now here we apply the heat intentionally and to make it to go through the process of the crystallization. We're changing the structure. through the heat treat. The proportion of a crystalline phase range is 90% to 98%. Remainder of the remainder are vitreous material. Remember, we talked about the phase range, phase diagrams before. The grain size significantly smaller than conventional ceramics. Of course, this is also make the glass ceramics much stronger than the ceramics that we can produce from other material. So, due to crystal structure, we can also have the glass ceramics that are not see-through, they're not opaque anymore, and they're either gray or white, and we can add color to it by using other compounds, but they're not clear in this case anymore. So how can we process glass ceramics? Heating and forming techniques, we use that in forming in glass working. Of course, this is going to create the shape of the product. Then we cool it off and reheat it, and as a result, we are forming what we call a dense network of crystal nuclei to form throughout, and that's really how it's done to make glass ceramics. Nucleation is actually the result. It results from small amounts of nucleating agents. What are some of those? TiO2, P2O5, and ZrO2. These are some of the what we call the nucleating agents. These are engineering terms. Of course, you may not be able to find them in any language English dictionary, but this is our vocabulary that we use in engineering, nucleating agents. And there are, of course, the heat treatment here would be done after the beginning of the nucleation, and of course, because we use this heat treatment, we increase the temperature to a much higher temperature, and it is going to cause a growth of crystalline phases. That's how it makes it denser and denser, and how we can increase the strength, really. So what are some of the advantages of glass ceramics? They are efficient. So efficiency of processing in the glassy state. Again, we're looking at it from the point of view of processing the material. So efficiency there means least amount of energy used, least amount of time used, and least amount of work that needs to be done. Those are really the bottom line of efficiency in material processing. The more time, the more money, the more people that are involved, the more lengthier the process. That means more equipment, more time, more labor. It becomes labor intensive. It makes it expensive. So like any other material that we would like to produce, we are concerned with the efficiency of the material. The dimensional control is much easier over the final shape of the glass ceramics. There are certain mechanical and physical properties of glass ceramics that we like to have as opposed to regular glass or the opaque glass, and that is the high strength, stronger than glass, absence of they're less porous, the absence of porosity. They have low thermal expansion. We like that because the heat gradient, we would like to make the slope of it as less as possible. The low thermal expansion is something that is highly desirable, of course, depending on the application. And also the thermal shock of glass ceramics. They are pretty high, or what we call, they have high resistance to thermal shock. So these are some of the advantages of glass ceramics. So where do we apply glass ceramics? Now remember, we made this dense structure that has a good heat resistance properties. Now we're going to use them at places that we need a material that can resist high temperature. The cookware is a good example that I put here. And anytime you want to have a good material as a heat exchanger, we do that. And we also use it in missile applications. So these are some of the applications of glass ceramics. Okay, so let's move on. Some of the discuss some of the elements related to ceramics. There are two forms of alternative forms of engineering and commercial importance of the material carbon. One is in graphite, the other one is the diamond. So there are also other elements related to ceramics. Now we call it related to ceramics because they're not really ceramics, but we apply it in the processing of ceramics. And it's important for us to take a look at some of those elements. Silicon and boron is also another important elements. The carbon, silicon, and boron, again, as I mentioned, they're not ceramic materials, so don't get them confused with the ceramic materials, but they are important when we develop them. They also compete for applications with ceramics, but they have important applications themselves. Since we're not going to discuss too many of these, then I thought maybe we should discuss these here for the sake of completing our discussion. So let's talk about graphite. Graphite is a form of carbon. It has a high content of crystalline carbon, and they're in layers, in the form of layers. Of course, there are certain advantage of having that in layers, and that is the bonding between the atoms. In layers is much stronger than the van der Waals force that I'm sure you guys have talked about it in your chemistry class, or well, mostly in the chemistry class. That should be covered. So the van der Waals forces there are weak. However, if we have the bonding between atoms in layers, they are covalent and strong. One of the problems that we have here is that these parallel layers are now bonded to each other by the weakness of the van der Waals forces. They're weaker, and it provides the layers that are covalent and strong, and that is more desirable. So I'm sure you guys know the difference between isotropic and anisotropic. We also had some discussions with some of you guys on the discussion board. So the structure makes graphite properties anisotropic, and something that is desirable in some applications in which we want the strength of the material in one direction to be stronger than the other. Not just due to the geometry, but also due to the very own nature of the material. And that can be achieved by different types of bonds between these layers and so on. So graphite is very important because as a powder, it is a lubricant, but in traditional solid form, it is a refractory, a very important and interesting application. Now, as a fiber, it has a high strength, and that's why it is used in fiber reinforced plastics. How's that? Great, right? So, did you guys know that the graphite is also used as a fiber in fiber reinforced plastics? Well, think about that. And let me move on to a more expensive material here, and that is diamond. Now, diamond is really nothing but carbon. It's carbon with a cubic crystalline structure with a covalent bonding between atoms between the atoms. So this covalent bonding causes that hardness that we have in diamond. It is a very hard material. The applications of diamond for that particular reason, high hardness, would be in the cutting tools. We use diamond blades to actually cut other material with, and that's why we use them on cutting tools, grinding wheels for machining hard, and of course we are going to use it anywhere that we need really a tough and very hard material. And of course we use that to sharpen grinding wheels and so on. So we start producing synthetic diamonds as back as 1950s. That's really when the synthetic diamonds were started. In this process, a diamond could be fabricated by heating the graphite to around 3,000 degrees Celsius or 5,400 degrees Fahrenheit under very high pressure. So high temperature, high pressure, it's going to produce diamond. Here's an example of a synthetically produced diamond powder. This is courtesy of GE, the Super Abrasives, the General Electric company, and just for you guys to have an idea what it looks like. The silicon is also a very important material to be discussed here. So I dedicated 3 slides to talk about silicon. Silicon is a semi-metallic element. It has it's a semi-metallic element in the same periodic table group as carbon, and it is one of the most abundant element in Earth's crust, about 26%, give or take, by weight. Silicon develops naturally, only as chemical compound. It can be found in rocks, sand, clay, and in general in soil. It is available in the form of silicon oxide or more complex silicate compounds. There are some properties that makes it very attractive for some of the applications, including their hardness, their brittleness. They have a light weight, they're chemically inactive at room temperatures, and they are classified as a semiconductor. Probably heard Silicon Valley in California. We're going to get into some of those applications shortly. There we are. So let's take a look at applications, some of the applications and importance of silicon. It is pretty much used as in manufacturing they're as ceramics in manufacturing. They're used as ceramics, SiO2. We talk about this in glass and silicates in clays. They are alloying elements in some of the steel that we've already discussed, cast iron. These are metals, aluminum, and copper. So we've already taken a look at those. Pure silicon is of significant technological importance in semiconductor manufacturing. The vast majority of the circuits, integrated circuits that are produced today, they are made from silicon. So the application in the electronic industry is vast. I don't have the exact numbers, but I know that the majority of integrated circuits that are produced today, they are made from silicon. So very important material. And last but not least, let's talk about boron. It's also a semi-metallic element in same periodic group as aluminum. It comprises only about a small amount of Earth's crust by weight. Now, 0.001% of Earth's crust by weight is still a large number. But if you were to compare it to the other two material that we just discussed, of course, it would be much less. It is usually occurring as minerals, borax, and the formula is presented here. I'm not going to go through that. I just need to know what it is. And kernite formula is pretty close. The left part of the formula, Na2B4O7, is actually the same. It's the amount of water. One is 10H2, the other one is 4H2. The molecule is, in one is more, in one is less, and that's what makes them to be of the same family. Some of the properties, they're lightweight. They are, again, semiconductors. It has semiconducting properties. They have high modulus of elasticity in fiber form and so on. Applications are in certain glasses as nitride for cutting tools, and of course in nearly pure form as a fiber in polymer matrix composites that are used. These fibers are used in fabrics. These fabrics are then used they are wrapped around the structures, walls, columns, and they're applied in civil infrastructure in which the replacement is not an option, but rehabilitation is. One of the biggest disadvantages of that right now is the cost. It's really not a disadvantage. It's one of the setbacks, and as the industry is working on it, producing it more and more, looking for more efficient ways, the cost goes down. And this is though the wave of the future. It started in the 50s, 60s, 70s. It took into 80s, and now they are applied more and more. So boron B2O3, it is used as a fiber in polymer matrix composite. That brings me to my today's discussion. As always, if you have any questions or comments, make sure to send them to me via the course website. Thank you.